Hello, my name is Roshene McCool. I am a Market and Technology Development Manager at Corning Optical, Fibre and Cable. And today I'd like to talk to you about the role of optical fibre at its 50-year anniversary. So this year, fibre is 50 years old. And I'd like to talk a little bit about the legacy of fibre, but also look forward and think about what its role in the future might be. So fibre's 50 this year, that's just 1 year older than I am. And in this 50th year, I have been both thinking about the legacy that fibre has over the past 50 years, but also thinking about what's its role in future networks. What are the important attributes of fibre that have been important in the past, and will they continue to be important in the future? And so what I hope to do in this presentation is to persuade you that the fibre attributes that have been important in the past continue to be important today and will continue to be important in the future. So let's start with the fibre legacy. So as I said, fibre is 50 this year, and it has been a key component in the growth of telecommunications. In 1970, Corning scientists developed the first low-loss optical fibre. In 1983, Corning Fibre was installed in the very first long-haul network connecting New York to Washington, D.C. And in 1989, that Corning Fibre was installed in submarine networks for the first time. Now, of course, what mattered in these networks was low attenuation, because these were long-haul networks utilizing the fibre attribute of low attenuation to deliver long-distance telecommunications signal transmission. In 1998, Corning released Leaf, which was another long-haul fibre, but this time allowing networks to go even further and even faster. And the fibre attributes that mattered in Leaf were, of course, low attenuation, because these were long-haul networks, but also low dispersion, because we were looking at dense WDM networks at this point in time. And also large effective area, because these were not only many wavelengths, but amplified networks. As fibre started to push towards the subscriber and fibre to the home networks, Corning released Clear Curve fibre, which was a bend resilience fibre. So the attribute that mattered here was a bend resilience against macro bend, because in these fibre to the home networks, there were so many connections that bend resilience helped deliver efficient networks. In 2012, Corning released SMF28 Ultra Fibre. This was a fibre that combined a number of attributes that mattered to deliver efficiently in these networks. And they included low attenuation, reach, bend resilience to avoid error with lots of connections, and also mode field diameter compatibility. Now here what we're thinking about is the ability of a fibre to connect to existing networks. Mode field diameter mismatch can create errors or ambiguity on test. And so the fact that this fibre had a 9.2 micron mode field diameter, which was the same as the fibre already installed, was a massive benefit in these metro and access networks. Furthermore, in 2015, Corning released SMF28 Ultra 200 micron fibre. This had a smaller outer diameter to support higher density of fibre in cables. So here, that low fibre OD, that mattered. So if we think about, well, what happened in the past, what's happening right now? Well, it is an observable fact that fibre connectivity is expanding into all network technologies, into fixed line access, into mobile access, and into data centre interconnect. In 2017, Corning delivered its 1 billionth kilometre of optical fibre. So what's driving this growth in fibre connectivity? Well, of course, it's the growth in consumer bandwidth and in consumer connections. But I think there's something more fundamental going on here, that there is a fundamental human need to connect, and that there are opportunities that come with that connection. So let's think about growth in consumer bandwidth. 85% of consumers are now using video calling. It's the second most important way of connecting with our friends and family after voice calls. 70% of users said that being connected now is important and that it would continue to be important in the future. Broadband speeds will more than double by 2024, and 75% of the IP devices will be in the access market. So this is really a true consumer information revolution. The expectation is that mobile subscriptions will increase by 800 million worldwide by 2024, and over the same period, fibre to the home and fibre to the building subscribers will increase by 200 million worldwide. So what matters then in terms of network connectivity growth and bandwidth growth, when we see these drivers, what matters within the network? Well, of course, efficient network installation and operation matters, the efficient use of existing infrastructure matters, and an increase in network capacity. And the fundamental keystone component in all of this is the fibre within the network. So what does that fibre need to deliver? Well, it needs to be compatible in order to avoid errors in installation. We need to reduce macroband errors on installation to avoid rework. In order to deliver efficiently in the existing infrastructure, we need to deliver more pathways for the same space, and you will hear I'm sure about the density trend, the density of fibre within the cable. And of course, we want network reach, because the further our network can reach, the more subscribers we can capture. In terms of network capacity, we can deliver that with wavelength division multiplexing. We can deliver it with space division multiplexing, where we simply put more fibres in the same space. And again, that's associated with the density trend and, of course, higher bit rate. So if the fibre is the keystone component of all of this, do the fibre attributes that were important before remain the same? Well, low OD matters for density. Low fibre attenuation matters for network reach. When we have high bit rates and when we have wavelength division multiplexing, we want that low attenuation across a broad spectrum of wavelengths. Low fibre dispersion matters at high bit rates, and also when we have wavelength division multiplexing. Fibre bend resilience matters to avoid macroband errors on installation, and also when we're looking at high density. And for compatibility, we still need that mode field diameter compatibility so that we can connect into existing networks. So if those attributes mattered yesterday and they matter today, then what about tomorrow? Well, let's look at the fibre attributes in some of our that matter in some of our next generation short reach transmission technologies. I've just picked a few out there, and I'm going to go through each in turn to look at whether low fibre attenuation, fibre bend resilience, low fibre dispersion, low fibre OD, and mode field diameter still matter. Let's think about C&L band dense WDM direct detection systems. Now, when in my early days of working in telecommunications, these were the absolute limit in terms of transmission technologies. These were used in submarine systems, amplified long haul and submarine systems. But what we're seeing in the future is that these systems have become very well established in the industry, and then we're now seeing them more and more in metro and in access networks. Point-to-point links delivering high bandwidth, a lot of pathways in here, both in terms of the fibres within the cable for density, but also in terms of the wavelengths within the fibre itself, and also the speeds of transmission, which can be high in these systems. So what matters? Well, we want low fibre attenuation, not only because these systems have a wide spectrum of transmission and therefore you want low attenuation right across the C&L bands, but also because we don't want to be limited by network reach. Sometimes we don't want to put amplifiers within these links, and so the distance of the link is entirely specified by that fibre attenuation. We want fibre bend resilience because when macro bend happens, it is dominant in the C&L band. And so if we have a macro bend within these links, we're going to see link failures exactly where our wavelengths of transmission are. We want low fibre dispersion because although these links are on kind of long haul submarine, we still don't want to be limited by dispersion, especially at high bit rates. And we want low fibre OD, again, as I said earlier, for density. So all of these things matter for C&L band. We're also seeing in short reach links and in the access O-band wavelength division multiplexing systems. These are direct detection systems, they're directly modulated systems, and they're at high bit rates. And so whilst they're relatively short reach, they are often dispersion limited. And in this context, the range of lambda 0 wavelengths matters because these transmitters and receivers can often cope with negative dispersion because they're directly modulated and chirped often. But it's the positive dispersion that limits the link length. Obviously that lambda 0 value will define where the highest dispersion is within the wavelength range. In next generation PON systems, they're using wavelength division multiplexing and time division multiplexing in point to multipoint systems that include splitters in order to reach as many subscribers as is possible. Oftentimes they're using the C&L band. Do you want me to pick it up from there?
I don't know. That may be necessary. let's see if Neil can figure. Let's see if Neil can figure it out here. Well, Roshene, maybe we can. Maybe you can carry on.
I'll do this live then.
Thank you.
So we were talking about next generation PON systems and the fact that these are WDM and time division multiplexed systems. And so again, we care about the fibre attenuation because although the splitters will dominate the loss within those networks, the further we can reach with these networks, the more subscribers we can cover. And that will increase the efficiency of the PON that we can deliver. Because these are in the wavelengths of these systems are often in the C and L band, that means that when we see a bend, that will be in the wavelengths of transmission, and that will create errors. And so we want a fibre that's resilient to bend for these kind of applications. Now, in many networks, as we see the increase in endpoint connectivity, we are also seeing an increase in inline monitoring systems, and this is an operational feature that carriers want and need in order that they can easily identify where they've got errors within the network. And here, these systems are their OTDR-based systems, and they operate at 1625 or 1650 nanometers. And of course, it's at those wavelengths that a macro bend will be at its very worst. So even if there's a macro bend within the network which isn't affecting the transmission wavelengths, it will certainly flag an error within the monitoring system because it will be at its highest loss there. We also care about mode field diameter compatibility because we know that when we splice two fibers together with different mode field diameters, we can often see a difference in the two-way measurement with the OTDR. So one way we might see an exaggerated loss, and if we measure from the opposite direction, we might see an exaggerated gain, and that's associated with the mismatch at the interface between fibers with different mode field diameters. And so for really efficient operations, then having a compatible mode field diameter is important in this context. So I've been through all of the next generation, or a selection, I shouldn't say all, a selection of next generation transmission technologies. And all of the attributes that I talked about previously matter for these transmission technologies. And so what was important yesterday and remains important today, we think will continue to be important tomorrow. Of course, Corning have a suite of optical fibers, but in the context of our broad load fibers, we have SMF28 Ultra and SMF28 Ultra 200. These are fibers with low loss. They have a 9.2 micron mode field diameter, which means they're compatible with the existing installed plant. They have a G657A1 standard macro bend, and in fact exceed that standard by some degree. And they have a slightly tightened lambda 0 wavelength range in comparison to the G652D specification, and the dispersion slope there is compliant with G652D. And so this combination of attributes means that these fibers are well placed to serve the networks of today and also the networks of the future. So as I said, it's 50 years of fibre this year. And I hope that in this talk, I've persuaded you that the fibre attributes, and not just singularly a fibre attribute, but the combination of fibre attributes of low loss, macro bend resilience, mode field diameter compatibility, and dispersion, all matter for networks of the future. And so that's me done there.
Roshene, I really appreciate the flexibility in coming in the last couple of slides live. Thank you. I got to say that I feel the most exciting piece was the bend insensitive. the clear curve. I mean, we treat it in the field environment, we treat it like copper. We staple it, we run it around corners. I don't know if you notice during the COVID when it first started, one of the things that we did was the inside ONT and fiber. Here's how important it became. We couldn't go inside the home, so we delivered ONT in a box, and we said, throw this piece of fiber out of the window and close your window and you can lock it. And we did a number of testing, but we were able to turn people up by throwing a fiber out of the window or to the door, and they were still able to close it and lock it for security reasons and everything else. And we were able to turn up customers with clear curve because, again, of that bend insensitive. So important to the industry.
Yes.
One question for you. I know there are some that came in, but one question for you is the 200 versus 250. When do you think we'll see the industry adopt that? What's your opinion on this? I mean, because obviously some folks already have data center interconnect guys, and where density is really, really important. Will we see the entire industry move that way? There doesn't seem to be any downside, but yet it is, why, how long do you think it'll take? And are there any obstacles that you're aware of?
So I agree with you. I don't think there are any downsides going to 200 micron. Those fibers have been designed to behave and to perform just as well as the 250 version. What we're starting to see is the necessity of density means that carriers who might be initially resistant to change have to implement those higher density cables which utilize the lower OD fibers, and in doing so they get more familiar with that form factor, and then are more kind of amenable, if you like, to more change as it progresses. But I do think the proliferation of endpoints, the increase in bandwidth, everything is driving towards density, because our colleagues in the transmission, they're doing fantastic work in getting more bandwidth down a single fiber. But in the end, you cannot get away from the fact that every connection is one connection. And the practicalities of bringing all those connections together inevitably means there is going to be density and more fiber in the network.
Great insight. Great insight. Thank you again, Roshene. I really appreciate that.